Hello everyone, my name is Ismail Amiri and this video is my final project for Math 355 with Professor Register at American River College. Now this video focuses on the relationship between the smooth blood flow and turbulent flow caused by the narrowing of the arteries. Blood flow is the movement of blood through the body. The heart pumps oxygen-rich blood through arteries to the body, delivering nutrition and oxygen. Veins carry oxygen-poor blood back to the heart, which sends it to the lungs to pick up more oxygen. Then the cycle repeats. It's like a delivery system, keeping the body healthy and alive. So the question is, how does the narrowing of the arteries during heart disease affect the blood flow, and what can mathematics teach us about this process? Coronary artery stenosis is a narrowing of the blood vessels that supplies oxygen to the heart. It reduces blood flow, which causes chest pain or leads to heart attack in severe cases. It is often caused by a buildup of fatty deposits or plaque in the arteries. If a blood clot from the coronary artery breaks loose, it can travel through the bloodstream and block smaller arteries in the heart, brain, or lungs. This can lead to a heart attack, a stroke, or a dangerous condition called pulmonary embolism. It is a serious situation that needs an urgent medical care, and if not treated in time, it can lead to severe complications that could be permanent. A study posted in the National Library of Medicine, the data suggests that 8% of all ischemic strokes were associated with the extracranial internal carotid artery stenosis. Here is another study from the National Library of Medicine. This study examines how blood flow in coronary arteries changes as they narrow due to the blockages, focusing on the transition from a smooth to turbulent flow and its impacts on the artery walls. Using conceptual fluid dynamics techniques, specifically on the transitional shear stress transport turbulent model, researchers analyzed varying levels of blockages like 0%, 30%, 50%, and 70% to measure factors like wall shear stress. This method provides insight into how turbulence influences blood flow, improving predictions for managing heart disease in clinical settings. The governing equations used in this study are based on Navier-Stokes equation, which describes the flow of blood through coronary arteries. The continuity equation ensures the mass conservation, which is the amount of blood entering and leaving a section of the artery remains balanced, and momentum equation that is derived from the Newton's second law describes how blood moves through the arteries, accounting for factors like velocity, pressure, and viscosity. Let's jump into the calculations. Here's a study of a fluid dynamics of a coronary artery stenosis, which we have the properties of a canine coronary artery. This model provides us the necessary data to calculate. Reynolds number calculates whether the blood flow is laminar or turbulent. The equation is Reynolds numbers equals rho times V times T over mu. Rho is the fluid density, which we have 1 grams per milliliter, that is also equal to 1000 kilograms per cubic meter. V is the average velocity of a fluid. V is the average velocity of fluid that we need to find. D is the diameter of the vessel, which is 6 centimeters in this model, and that is variable due to the stenosis. Mu is viscosity of the fluid, which is 3 times 10 to the power of -3 Pascal per second. We are now calculating the average velocity from the flow rate that is given on the model, which equals to 18 cubic centimeters per second equals to 18 times 10 to the power of -6 cubic meters per second. And to find the area, we can calculate as area equals pi multiplied by the square of half the diameter. And now we are going to substitute our numbers where the D is equal to 0.06 meters. Now we plug in our numbers and we get pi times 0.03 square. And our final answer is 0.002827 square meters. Now, to calculate the velocity, we use the equation V equals the rate of flow over area. Now we substitute our numbers. We have the rate of flow and the area. So we plug in our numbers and get us the final answer at 0.00637 meters per second. Now to find the Raynaud numbers, we plug in our necessary numbers into the formula and then we get our final answer, which in this case we have 127.4. Since the value of the Reynolds number is less than 2000, it is considered to be laminar flow. Now anything above 2000 is considered to be turbulent. Now that we know our flow is laminar, let's calculate the wall shear stress in a coronary artery. It is a force that is exerted by the flowing of blood in the inner walls of the artery. Now it depends on the blood's viscosity and the velocity of flow near the wall. Wall shear stress plays a crucial role in maintaining a healthy blood vessels, but abnormal levels can lead to problems like atherosclerosis or a plaque buildup, which we earlier mentioned what type of complications it can create. The equation is wall shear stress equals to dynamic viscosity of fluid times the velocity gradient of the wall. Now, to calculate the velocity gradient of a cylindrical flow, we can estimate as the velocity gradient equals to 4 times Q, which is the rate of flow, over pi times the diameter cubic. So we're going to substitute our numbers and we get our answer that the wall shear stress equals to 0.318 millipascals. If the diameter reduces by 50%, which previously we had 0.06 meters, 50% reduction, it's gonna be 0.03 meters, and that will increase the wall shear stress to 2.54 millipascals. Now this proves that the more a diameter reduces by the stenosis or the artery blockage, the more pressure there will be. For treating these blockages, doctors treat the coronary artery blockages with the stent using a procedure called angioplasty. They insert a thin tube with a balloon into the blood vessels, guide it to the blocked artery, and inflate it. Now, once it's inflated, they will place a stent and then they will inflate the balloon so the stent will remain there and it will keep the flow as normal and laminar.